These are my predictions for paper 1 OCR A-level chemistry A exam 2025. In this video, I will focus on the topics that are most likely to be in the exam, and I will tell you what type of question should you expect within these topics. So the first topic is the enthalpy change, which is one of the very common questions or very common topics in paper 1. So they provide you with the calorimetry experiment, whether it's for combustion or for a solution, and or even for a neutralization reaction. And then they ask you to calculate the enthalpy change. So you're going to use the equation Q equals MC delta T, and then you're going to use the value of the Q in kilojoule this time to calculate the enthalpy change, which equals delta Q over moles. Few things that you need to be aware of when you do this calculation is to take note of whether the reaction is actually exothermic or endothermic, and account for that when you calculate the delta H. So any combustion is going to be an exothermic reaction. If there is an increase in the temperature, it's going to be an exothermic, and if there is a decrease in the temperature, it's going to be an endothermic reaction. If it's exothermic, remember that the delta H is going to be with a negative sign. So when you do the final calculation for the Q over the moles, you need to put it with a negative sign to have the delta H with a negative sign. Also, the Q from the first equation we calculated in joules. So in the second one, we need when we calculate the delta H, we need to convert that into kilojoules. And also calculation of the delta H using bond energies. This is quite common in the multiple choice questions. Thermodynamics, one of the very common topics, and usually at least two of the following will be in your exam because they are always in the exam. The first one is the Born-Haber cycle and the calculation of the enthalpy of lattice formation. So you would need to complete the cycle with all of the steps, the atomization, the ionization of the metal and electron affinity, and finally the enthalpy of lattice formation. And don't forget at the beginning the enthalpy of formation. Accompanied with that is the Hess cycle. So Hess cycle is quite common in paper 1, and in Hess cycle it's either using the standard enthalpy of formation or the standard enthalpy of combustion. So one of the enthalpy changes for the arrows for the cycle will be missing, and you just need to construct the Hess cycle and calculate the missing one. And then the entropy change, this is very common in your exam, and the questions usually come either to predict the entropy change, whether it's going to be positive or negative, and I will talk in a minute about how to reach that conclusion, mostly in the multiple choice questions. Or to calculate the entropy change based on the standard entropy of the products and reactant. And if we talk about entropy change, there will always be a question about the Gibbs free energy, which links the enthalpy change to the entropy change. So Gibbs free energy, which is delta G equals delta H minus T delta times delta S. And of course, they're going to ask about the reaction feasibility, because for a reaction to be feasible, the value of delta G has to be a negative or in the minus. So the minimum temperature needed for a reaction to be feasible, we will put delta G to be with a 0 value, and the temperature will equal delta H over delta X. Sometimes they give you a graph like this one on the right-hand side of the slide here, which gives you the relation between delta G and the temperature. As we can see from this equation, the delta S here is actually the gradient, or the gradient is minus delta S. And then the delta H will be the y-intercept. Mostly you're gonna calculate the delta S from the gradient, so you need to find the gradient of the graph, and the delta H you can use the equation and then calculate the delta H from this equation. So what are the factors that affect the entropy and how can you predict whether the entropy change is going to be positive or not? The first one is the physical state. So because entropy is the degree of randomness or disorder of the system. So the more the disorder, the more the entropy of the system. So if you have more gases on the product side than on the reactant side, then you would expect delta S to be positive, or you would expect the value of the entropy for the products would to be higher than the reactant, because remember that delta S will equal the total standard entropy for all of the products minus the total of the entropy for all of the reactants. And then we have the number of particles. So if you get more particles on the right-hand side or for the products, then that means there will be more entropy on the right-hand side, or for the for the products, which means the entropy change will be positive. Remember that this is linked with the chelation effect that we see with the complex ions for the transition metals, where chelation is when a bidentate ligand or multidentate ligand substitute a monodentate ligand to give you a more stable complex, and this is because of the formation of more particles or formation of more moles of the on the products hand side. So there is more entropy, there is an increase in the entropy, and the entropy change is positive. And finally, the solution. So dissolving a solid in water will increase the entropy. This is why solubility of some ionic compounds in water, for example, is exothermic, is endothermic, but as the solid still dissolves, this is because of the increase in the entropy. Reaction rate and order calculation. This is one of the very common topics in paper one. The question mostly comes in the form of a table with several reactants and the reaction, the initial rate, and they ask you to calculate the rate or to find the rate and the order in terms of the different reactants and provide evidence from the data provided. So you have to calculate the order for each of the reactants. A reaction half-life, this is mostly in the multiple choice question. And remember that the reaction half-life is independent of the concentration of the reactant for a first order reaction. And the half-life can be calculated from the natural logarithm of 2 over k, which is the rate constant, or 0.693 over k. In case of zero order, so there's the half-life will decrease as the concentration decreases, and for second order, it will increase as the concentration decrease. So the question could come like, this is the half-life of this particular reaction, which is first order. How would the half-life be if we change the concentration from this value to that value? If it's a first order, then there is no change in the half-life. So when we calculate the order of the reaction, remember that zero order means the rate doesn't change if the concentration changes. So it's a straight line. It always have the same gradient. If it's first order, the rate will change, will be directly proportional to the concentration. If it's second order, the rate will be directly proportional to the concentration squared. So to calculate the order, all concentrations are kept the same and one reactant only changes. If there is no change in the rate when you change one of these, then it's zero order. If the change is the same, so it's doubled for both of one of the reactants and the reaction rate, then it's first order. And if the concentration changes by a factor of x, causes a change in the rate by a factor of x squared, then it's second order. And the x or the factor of the change can be calculated from the new concentration over the original concentration. And don't forget the rate determining step, which is the step that has all the reactants that affect the rate. So something like this one, where the rate of the reaction is second order for A and first order for B. As we can see, they usually will provide you with the concentration here for reactant 1 and 2 with the rate. And then if they're going to change only one, so here we changed A and kept B the same. As you can see, when A changed by a factor of 1.5, the rate changed by a factor of 1.5 squared. and you can carry on. So the second one, they changed both. So we know that for reactant A, it's first order, and for reactant B, we need to find how will it be for reactant B. It's, sorry, for A, it's second order. So the change here will be the factor of the change of A squared times the factor of the change of B because it's first order. So when you do this, usually they ask you to provide evidence from the table. How did you reach that relation? Or how did you reach the order in terms of for all of the reactants? So this is how you're gonna do it in your exam to get the full marks on that question. Topic 4 is the reversible reactions and equilibrium constant. So this is very common in paper 1, both at an extended question and also sometimes in the multiple choice questions. They would ask you to calculate the Kp for gaseous reaction. The most of the reaction they bring in the exam are gaseous reaction. So Kp is the equilibrium constant for the gaseous reaction, which depends on the partial pressure. So it equals the product of the partial pressure of the products, each raised to the power of their number of moles, divided by the partial pressure of the reactants, also raised to the power of their number of moles. Kc is for the concentration, so it's exactly the same, but instead of using partial pressure, we use the concentration. Remember the different factors affecting the position of equilibrium. That's very common in the exam as well, and they tend to ask about the pressure and temperature. So temperature will depend on which side is exothermic, which one is endothermic, and the pressure will depend on the number of moles of the gases on the right and left hand side of the reaction. Topic 5 is pH and buffers. So this is also very, very common in paper 1. Usually never seen paper 1 without questions about the pH. And sometimes they ask about buffers as well. So they would ask you to calculate the pH of a different acid or a base, or they could ask you to calculate the Ka for the weak acid. So remember these, all of these equations that you would need to use in your exam, or at least use some of them in your exam. So pH is minus log 10 of the hydrogen ion concentration. For any acid, the concentration of the acid will equal, the hydrogen ion concentration will equal the concentration of the acid if it's monoprotic. If it's diprotic, it's going to be 2 times the concentration of the acid. In case of water, so the ionic product for water equals the hydrogen ion concentration times the hydroxide ion concentration. And for neutral water, the hydrogen ion concentration will always equal the hydroxide ion concentration. So it's very common to ask you why pure water is neutral. This is because the concentration of the hydroxide ion and hydrogen ion are always the same. And to find the concentration of the hydrogen ion, usually they provide you with the Kw or the ionic product at different temperatures and ask you to calculate the pH. So you need to find the hydrogen ion concentration, which is going to equal the square root of Kw. And then for bases, then hydrogen ion concentration will equal the ionic product for water divided by the concentration of the base. So we're basically using the same equation here, but the hydroxide ion concentration here is going to be the concentration of the base. And then for weak acids, so we know the dissociation constant for acid, the Ka, will equal the concentration of the hydrogen ion times the concentration of the anion divided by the concentration of the acid. Normally, we take the concentration of the acid as the initial concentration, even though we should be calculating that for the equilibrium concentration. But because acids are very slightly dissociate, so there is a small change in the concentration of the acid at equilibrium. So of course, the concentration of the hydrogen ion will be the same as the concentration of the anion. So you can find the concentration of the hydrogen ion at the square root of Ka times the acid concentration. And finally, for buffers, so buffers will have both the acid and a salt, or sometimes with a base. And then to calculate the hydrogen ion concentration for the buffer and the pH of the buffer, then this will equal the Ka of the weak acid times the concentration of the acid divided by the concentration of the anion, or if it's a base, if we add a base, then it's going to be divided by the concentration of the base. Electrochemical cells and electrode potential. So usually I see this question in the multiple choice where they ask you to calculate the EMF. However, the standard electrode potential is used all over the exam, especially with any redox reaction. So they might provide you with the standard electrode potential for two different reaction and ask you to predict which one is going to be oxidation, which one is going to be the reduction. So sometimes as well, they ask you to set up an electrochemical cell. So you need to know how to set up the electrochemical cell and calculate the EMF. So remember that oxidation, the one that will undergo oxidation, or the species that will undergo the oxidation, is the one that will have more negative E node or more negative electrode potential, or a smaller value for the electrode potential. It usually takes place at the anode or the negative electrode, while the reduction it's a more positive, or the one which is going to have a more positive E node value, or a larger value for the standard electrode potential. And that will take place at the cathode or the positive electrode. When you calculate the EMF, it will equal the standard electrode potential for the reduced species minus the one that will be oxidized. Remember that the standard electrode potential they usually provide you with is the one for the reduction. And sometimes, although in the exam they wouldn't give you a table like this one, like an electrochemical series for so many different reactions, but they could provide you with two or three different reactions, reduction with their standard electrode potential, and they could ask you why this particular species can reduce this but not the other one, and then you're going to use the values of the standard electrode potential to put your answer. For example, here the vanadium 3 to vanadium 2 has a higher standard electrode potential than the zinc plus 2 zinc. That means zinc can reduce the vanadium. So this is how you're going to answer this. But zinc, for example, cannot reduce the vanadium 2 plus to vanadium because the standard electrode potential here is lower than the one for the zinc. Transition metal complex and complex ions and the reactions, the very common in paper one, at least one extended question about that. So you need to know understand what is meant by transition metals, because it's quite common to ask you what is meant by transition metals. Remember that transition metals, not just that they have their outer shell electrons in the d subshell, but they must have more than one ion formed, and their ions will have incomplete d shell. This is why zinc and scandium are not transition metals, even though they are in the d block in the periodic table, because zinc will form only one ion, which is zinc 2 plus. This is due to the loss of 2 electrons from the 4s, and it has a full d subshell. And scandium is the same, so it loses 3 electrons. It gives you only one ion, which is scandium 3 plus, and the electrons lost are from 4s and the 1d, so it has a completely empty d subshell. Ligand substitution and precipitation reactions for ligands of ligand and also the aqua-ions. So these are very, very common questions, and you need to memorize all the color changes due to ligand substitution or the precipitation reactions. So this is very common in paper one, so please make sure that you know all of these, or due to the change in the oxidation state of the central atom as well, or the central ion. The isomerism of the complex ions, both the cis and trans and optical isomers, are very common. One of the most common ones are these isomers, which are produced from two of the bidentate ligands with two of the monodentate ligands. And then they would ask you to draw all the isomers that can be formed. So here we have three different isomers. So we have two of these as the cis isomers, and the cis isomer will come when the two monodentate ligands are on one side. And this can result in two of the optical isomers, which are mirror image non-superimposable isomers. And then we have the trans trans isomer where the two monodentate ligands are opposite to each other. So in this case, this is symmetrical. This one doesn't have any optical isomer. So you're gonna ask you to draw all the three isomers here. And these are the main transition metals that you need to know and to memorize their reactions and their colors. These are iron 2 plus, iron 3 plus, the copper 2 plus, chromium 3 plus, and manganese 2 plus. So please try to memorize the color of the aqua ion, their solutions and their reactions, the color of the product for the precipitation, and any changes when we add excess of the hydroxide or of the ammonia. So this table summarizes these reactions for you. Group 2, 7, and ionization energy. So the trend in the ionization energy is very, very common in paper 1, either as an extended question, a part of an extended question, or in the multiple choice questions. So there will always be something about the ionization energy. They like to ask about either the trend within group 2 as you go down, or they could ask across a period, or they could ask about the also the successive ionization energy, the change in the successive ionization energy. So this is very common, and they would ask you to explain the trend or explain why there is an increase or decrease in the ionization energy. So please remember the three factors that affect the ionization energy, which are the nuclear charge and the distance from the nucleus or the atomic radius and the shielding as well. The reactivity trend for both group 2 and group 7 as well, they sometimes come in the exam. So for group 2, remember reactivity is related to the ionization energy, so it increases as we go down due to the decrease in the ionization energy due to the same factors that affect the ionization energy. For group 7, the oxidation power of the halogens will decrease as we go down. So chlorine can displace the chloride, bromide and iodides from their salts, and bromide can displace the iodine, but not the iodide, but not the other way around. The chemical tests, so it's very important because if they don't come in the extended question, they would come in the multiple choice questions. So chemical test is specifically for the halides. So we can distinguish between the halides with the silver nitrate test, and then we can add the ammonia. So remember, the all of the halides will give you precipitate, not all of them because fluoride will not, but chloride, bromide, and iodide, they will all give you a precipitate. Chloride, white precipitate with silver nitrate, which is silver chloride. The bromide will give you the cream precipitate, or sometimes they call it off-white precipitate, which is silver bromide. And the iodide will give you yellow precipitate of silver iodide. To distinguish between these, you can use the ammonia. So if you use dilute ammonia, only the silver chloride will dissolve. If you use concentrated ammonia, the silver bromide and chloride will dissolve, but the silver iodide will not dissolve in any of these. Finally, adding chlorine to water. So we use chlorine to disinfect water, and this is because of the disproportionation reaction that happens when chlorine is added to water to give you the chloride and the chlorate one. So this is disproportionation where the chlorine has been oxidized and reduced. Titration and specifically back titration. This is one of the main questions or constant questions in paper 1. So the titration could be a simple acid-base titration, but it's a back titration. Or it could be one of these redox titration involving the transition metals. Remember that in back titration, you have to work from the down or from the bottom upwards. So they're going to tell you the steps for the titration where they add excess, for example, of a base to an acid, and then they're going to titrate the excess base. So you need to start working from the last step going upwards. So it's almost a guaranteed question. And please make sure that you answer these questions from the past paper. Make sure that you know the exam technique and how to do these calculation correctly. Then we have the multiple choice. So the exam will start with 15 multiple choice. There are certain topics that are more common in multiple choice. So first of all, usually the multiple choice starts with 2 or 3 questions from the amount of substance topic. So things like calculating or finding the empirical formula or calculating percentage of the composition of something in a certain solid, or any of these simple calculations, they usually come at the beginning. And then polarity of molecules. So this is also one of the typical questions in the multiple choice section. So remember that the polarity, even though you may have polar bonds, but if the molecule is symmetrical, then it's not going to be polar, it's going to be non-polar. Enthalpy change using bond energy, as we've said before, predicting entropy and enthalpy change signs for a particular reaction. Usually these come in in the multiple choice. Calculation of the EMF as well, the half-life of the reaction, one of the topic ones, and then the Brunstad-Lowry acid bases. So remember that a Brunstad-Lowry acid is any species that can donate a proton, and a base is any species that can accept a proton. And then they might ask you as well about the conjugate base. So the conjugate base of the Brunstad-Lowry acid is the species formed after an acid donates a proton. So if you have something like hydrogen fluoride reacting with ammonia, for example, to give you the ammonium ion and the fluoride ion. So this is your conjugate base from the acid, and then this is the conjugate acid. So this is the conjugate acid from the ammonia from the base. So this is the Brunstad, the Lowry base. These topics are much less common. They don't come in the exam every year or that frequent. But remember, I'm not saying they will not be in the exam, because they may decide it's about time that we ask about these topics. So the Arrhenius equation, which links the rate of the reaction with the activation energy and temperature, Boltzmann distribution curve for the different factors affecting the rate of the reaction. Please make sure that you know how to draw the Boltzmann distribution curve for a reaction and how does it change with the changed factors. And then properties of ionic, metallic, and covalent bonds or covalent compounds. So things like the difference in the melting points and boiling points. So you need to refer the forces of attraction, and hydrogen fuel cells, and also shapes of molecules. So I want to finish this with final notes. So please remember that your exam is going to be math heavy. So make sure that you know all your equations and how to do all the calculations, because you're going to do a lot of calculations in your exam. Don't forget the chemical test for ions, both for anions, for cations,